Okay, well, welcome back. In this video, we're going to hit on one of the most foundational concepts in computing. All right, and this is binary number systems. Very essential topic, and I would expect that most of you, this would be a bit of a review. You've probably seen it before, but because it's such a foundational topic, such an important topic, I wanted to make sure that we had a video to go over it. So that you make sure that it's crystal clear as you move forward, because it's going to be used in countless courses down the road. So, well, binary number systems, let's take a moment and just think a little bit about why do we learn this? All right, why do we bother learning binary, right? Well, it has to do with something that I'm sure you've heard in countless science fiction and different places throughout your life, and the fact that computers, if we have a computer thinks in, and I'm a terrible drawer, so bear with me. But if we've got here, say we've got our someone having a laptop here, right? You've got your computer. Well, computers, how do they think? Well, they think in binary. They think in ones and zeros. Okay. As you get further along and you look at things like digital electronics, as well as like computer organization classes down the road, you're gonna get a better understanding of why and how that works. All right, but that's for another day. Okay, but us mere humans, right? We don't think in binary, right? We're thinking in something called decimal numbers, or AKA base 10, right? We're using digits 0 through 9, and the reason why is we've adapted through our lives to think that way, and societies have tend to have adopted base 10 number systems because we got 10 fingers, so it tends to be a good way for us to have been counting and adapting. So besides that, there's no real reason why it has to be using those digits to represent various ways of counting things and representing different numbers. Okay, so we think in base 10, we're used to that, that's how our brains operate. Computers think in binary, and we need a way of being able to go between these, where we're converting base 10, right, decimal numbers, to binary, also called base 2. Okay, base 2 because there's only two digits, 0 and 1, versus base 10 where there's 10, 0 through 9. Okay, we need to be able to know how to convert between those two. Okay. And that's what we're going to do. That's the focus of this video. Okay. And we'll do it in pieces where we'll first look at, say, taking decimal numbers, going to binary, and then we'll go the other direction. All right. So base 10, how does that work? Okay. Well, first, I just want to kind of point out that when we're talking about decimal numbers, right, it's coming from the Latin word decum, meaning 10. All right, so that's when we talk about decimal, it's a little bit of the origins of it. And so decimal in this context, right, we're saying decimal, we're talking about base 10, digits 0 through 9, right? And again, the only reason we're using that and we think that way is cultures have adapted these types of number systems because we have, say, 10 fingers and 10 toes, okay? And let's kind of go through a little bit of the obvious here. I want to show you an example where we take this number 212, I should say. Okay, 212, represented as a decimal number. Okay, and let's do something that we all just kind of do naturally without really even thinking that much because we're so used to it, that we know what 212 represents, because when we take that leftmost 2, right, we know that 2 on the left in the third place there, right, is effectively represents 200, or 2 times 10 squared, right? That represents 200. And the 1, right, represents 1 times 10 to the first, or 10, right? And the rightmost 2 is 2 times 10 to the raised to the 0, or 2, right? We add those digits together, we get our 212, right? So we know that, we're used to that, we do that all the time. All right, we do that quite naturally, right? Like again, if I kind of just did it out by hand, if we took a number, say 798, right? And I'm going to write it even like this with this little suffix here for DEC, for decimal, indicating that that is actually a base 10 number, right? And we know what that equals, right? We know that that equals 7 times 10 squared plus 9 times 10, right? Or 10, I'm gonna show the power just to kind of make it clear, plus 8 times 10 to the 0, or 8, right? And that's going to give us our 700 plus 90 plus 8, or 798, right? Now, wait, why am I doing that out, right? It seems so obvious. Well, just because when we look at binary numbers, it's the same idea, okay? It's the same idea, except instead of raising it based on powers of 10, we're doing it based on powers of 2, right? So don't overcomplicate this stuff. You know how to do it, right? You just got to take what you kind of do kind of automatically in your everyday life, and just kind of reflect how it's the same concept for binary numbers. Okay, so let's look at this example here. And what we're doing is we're taking a binary number and we're converting it to base 10. So if we look at our previous example here, right, what we're doing is we're doing this conversion here. We have a binary number and we want to convert it into a number that we are adapted to think, in base 10, how we're adapted to think, right? So we're going to take a binary number and we're going to convert it to a base 10 decimal number, okay? So if we look at a binary number, and by the way, one often thing we want to do, right, to avoid confusion, is this number, right, does not mean 1,101, right? It means something different, and that's often why we will either write bin for binary, right, or 2 for base 2, down as a little suffix down below, like almost like a subscript below the number, as a way of indicating that it is indeed a base 10 number, to not confuse it, in this case, with 1,101, right? Now, if you understand what we did before related to base 10 numbers, it's the same idea, except notice that the only thing that we're changing here is we are not using powers of 10, we are using powers of 2, right? If you get that, it's the same idea, right? And you will get really good over time with kind of knowing your powers of 2 off the top of your head, because you do them so frequently, right? So we do this, right? We say, well, what is this binary number in as a decimal number? Well, we're going to do 1 times 2 to the third, right? Plus 1 times 2 squared, plus 0. So this is going to just drop, right? Anytime we have a 0, that digit's just going to drop out. Right, and then we're going to have 1 times 2 to the 0 power, or 1. Right, we add those all together and we get 13 in base 10 decimal number. Okay, so this, in binary, is equivalent to 13 in base 10. All right. So let's do this. Let's take this example. Let's look at another example here. And let's do this in such a way that let's do a conversion just to kind of practice this a little bit more. Okay. Let's take a slightly different binary number. Okay. And let's take a look at how to convert this, right? One thing I want to point out is the zeros, they're gonna drop out. So there's kind of a shorthand to this, but I'll do it out the long way, right? We've got, right, 1, right, times 2 to the third, plus 0 times 2 squared, right, plus 1 times 2 squared. I'm sorry, 2, really just 2, plus 0 times 2 to the 0 power, right? These terms are going to drop out. So effectively what we have is 8 plus, and then we have here, we just have our 2, right? So this is going to be 10 in base 10. Okay. All right, so we did one path, right? We did one kind of path through this, and what we want to do next is we want to look at how we go the other direction, right? We want to say, well, what if we have a base 10 number and we want to convert that into a binary number? We need to know how to go that direction too, right? To go base 10 to binary. So let's go ahead, let's do that. Okay, so the number we're going to convert, the base 10 number that we're going to convert is 53. All right, and we're going to convert this 53 in base 10 to its binary equivalent. And this is where it's super helpful to know your powers of 2. All right, I'm going to put them here on the right so that we can reflect on them. We can look at them quite easily. All right, obviously, powers of 2, we're doubling, right, at each step along the way. Okay, so let's the way that we do this, right? And we're going to say we're doing an 8-bit binary number, so or 1 byte. So we have 8 bits, right? 8 ones and zeros, and keep in mind, right, that at each point, each digit here represents a certain power of 2. Okay, starting at 0. And the way that we want to approach this is we want to say, okay, we look at 53 and say, well, what is the largest power of 2 that is less than or equal to 53? Okay, the largest power of 2 that is less than or equal to 53, right? And if we do that, right, we're going to recognize that that power of 2 is 2 to the 5th, 32, right? Because if we go to 64, it's bigger than 53. So the first digit is 2 to the 5th, right? So what's going to happen is all the other digits to the left of that are going to be 0, okay? And 2 to the 5th is going to be 1. Okay. Now what we do, since we've now represented number 32, right, we're going to take our 53, we're going to subtract it by our 2 to the 5th, right, our 32, right, 2 to the 5th or 32, and we're going to say, well, what do we got left over, right? So we still have 21 left to represent, okay? We still have 21 left to represent, because we already represented 32, but we still have 21. So then we do the same thing. We say, well, what is the largest power of 2 that is less than or equal to 21? Well, in this case, right, 16 or 2 to the 4th, right? So that's going to be a 1. And then we're going to take our 21 minus our 2 to the 4th, right? And we've got 5 left, right? And again, this is in base 10 down here. Okay. Right, so we've got 5 left, and we're going to do the same thing. What is the largest power of 2 that is less than or equal to 5? Right, and this case, right, it's 2 squared. So 2 to the 3rd, or 8, is too big. We're going to make that a 0. Okay, and then 2 squared is going to be a 1. Right, we're going to say 5 minus 4, or 2 squared. Okay, we have 1 left. Right, and then we're last step here, we say, well, what's the largest power of 2 that's less than or equal to 1? 2 to the 0, right? So it's going to be 0, 1, and then effectively we have none left. We've represented everything, okay? So that's how we go from a base 10 decimal number to a binary number, and effectively what we've done, right, is we've now looked at through this video going both directions, right? Going how our brains think, to binary, and going from binary back to base 10. Okay. All right. Essential topic, you're going to see a lot. Okay, we want to focus on programming in here in this class, but this is relevant related to our next topic, which is data types. So we want to make sure that we're familiar with binary in the context of being able to understand how different data types are represented in our computers, so that we can use them as part of our programming logic. And that is the topic of the next video, so stay tuned and we'll cover that topic next.